Okay, so this is the next video in the sequence, and I'm looking at the Java stack slides that I've distributed via OneNote. And this is kind of interesting because it's talking about the way the Java virtual machine gives each method its own piece of memory, right? And the starting piece here is that the main method gets allocated some memory to hold the program counter information and the value of any variables that it uses. And in this case, it only uses the integer I, and it has a value 5. When that call to foo is made, then the method foo needs to know what's happening and needs to have memory to store its information. In particular, it needs to have memory to store j, and it needs to have memory to store k. And that gets pushed onto the stack, right? So that's the next thing on the stack after the memory allocated to main. And then you can see foo calls bar, and then bar needs memory allocated to it, and that memory gets also pushed onto the stack. Right, so that's getting pushed onto the stack. Now when we finish with bar, when we're done with bar is going to get popped, the memory associated with bar is going to get popped off the stack because we don't need it anymore. And then when we've finished with foo, the memory associated with foo is going to get popped off the stack because we don't need it anymore. And then finally, when the whole program exits, the memory allocated to main is also going to get popped off the stack. In fact, the whole stack's going to get unwound once we finish that particular program. Now, one thing that I did that was perhaps a little contrary is, in class, what I suggested is what happens if within bar we do a call back to foo, right? Well, what happens, right, if we do that call, we're going to get yet another copy, because it's a different instance of calling foo, right? And we need to know that have a value for j, or a memory area to store j, and we need to have a memory area to store k, right? And the trouble with that is now bar is going to be called again, and then foo is going to be called again, and then bar and foo, and there's no terminating condition, at least in what I've written there. So what happens in that instance is we're going to get a stack overflow. Now think about how long that might take, all right? You've got, let's say each piece of memory that we allocate on the stack is worth 8 bytes. It's probably more, but let's say it's 8 bytes. If your computer is a normal sort of computer, right? Let's make it a bit of a slow one, so it's running at 1 gigahertz. And let's just, for the sake of simplicity, assume you can do each of these calls in one clock cycle. You probably can't, but let's assume. So that means that every clock cycle you can do that call from foo to bar or bar to foo. So every second you're going to have 8 times 1 billion, so giga. So you're going to use up 8 gigabytes of RAM. So if your machine only has 32 gigabytes, you're going to use up all the memory on your machine within 4 seconds. Right? Now it's a little bit more complicated than that. There's probably more numbers and it'd probably get killed before it happens. But it's very quick. It'll happen very quickly. The other thing to note is that that Stack Overflow will have different effects depending on the context within which it's operating. If it's operating as a mobile app, probably all you'll see is the app just completely disappears, and you'll have to restart it. On a desktop or a laptop, what you may see is the whole machine rebooting, potentially going to a blue screen of death under Windows. Right, so you've got to be a little careful with that sort of thing. Okay, that's the last piece I want to talk about, the Java slides. I just want to have a quick talk about the C++ slides, but I'll do that in the